Hello everyone. Our today's topic for A-level chemistry 9701 subject code A-level chemistry is redox reaction. What are redox reactions? Those reactions in which oxidation and reduction both take place. Those are called as redox reactions. In the previous classes in O level, we have already learned about the oxidation and reduction processes. The loss of electron, then loss of hydrogen, gain of oxygen, or increase in oxidation state is considered as oxidation, and on the other hand, gain of electron, gain of hydrogen, and loss of oxygen, and then decrease in oxidation state is considered as a reduction. This we have already learned. Now, the redox reactions can be best explained by taking the redox titration. By considering redox titration, we know that we take in a burette a KMnO4 solution. In a burette, normally we take KMnO4 solution, and in the conical flask we take as just like ferrous sulfate solution, Fe positive 2 aqueous solution. Now, ferrous sulfate solution act as a reducing agent and KMnO4 act as a oxidizing agent. Now, half equation of both these can be mentioned here. For example, MnO4 negative in the presence of 8 protons gain 5 electrons and converted into Mn positive 2 forming 4 water molecule. This equation indicates here manganese has positive 7 oxidation state. It means that purple color is of this MnO4 solution is when this will be converted into Mn positive 2, it will become colorless. It means that there is no need in this reaction to use an indicator because the intense purple color of KMnO4 itself acts as an indicator, and when a very light pink color left behind, it means that is our endpoint. By using the formula C is equal to N by V, we can easily calculate the required volume of KMnO4 to oxidize the iron 2 solution completely. Now, if we take the values of electrode potential from the data booklet, we note that the value for KMnO4 solution is positive 1.52 volt, and for iron, with respect to the reduction, Fe positive 3 gain electron and change into Fe positive 2 ion, that has a value positive 0.77. But if we compare both of these values, it is quite clear that the value of KMnO4 is larger as compared to the value of iron Fe positive 3 reduction. So, this value, higher potential value, will turn this lower value into the reverse reaction, and reaction can be written as inverse. It means that now KMnO4 solution will compel this iron positive 2 ion to change into iron positive 3 ion by the loss of 1 electron. Now, the value will become automatically negative due to the oxidation process. Whenever we will add by equalizing the number of electron gained or lost, and if we add both of these equations, we will get the overall equation. But as a result, if we find the total electrode potential value, the difference on adding will comes 0. For example, 0.75 volt. Now, this much higher electrode potential value for this cell potential value, this much higher cell potential value indicates that a reaction can be carried out quite easily, and we will observe the change in color and the endpoint will be clarified. This titration can also be used to find out the total mass of iron Fe positive 2 ion in a particular type of salt or in a titration process. Now the same titration process can also be used using as a potassium dichromate 6 using as an oxidizing agent. If we compare the equation of dichromate with respect to this reaction as a reducing agent, then we can easily find out that the electrode potential value from the data booklet is quite easy. That is also positive 1.33. Now, the difference will comes less than those 0.77. It will becomes 6 and then 6.0. Sorry, for 0.56 volts. Now, this is also a positive value that is indicating that redox reaction can also be performed using dichromate solution and the iron solution as a reductant. It is quite clear from this equation that both of these can be used to convert. The titration with respect to the dichromate ion solution is more accurate because the solution of dichromate can be prepared to the more accuracy as compared to the aqueous solution prepared of KMnO4. So, using the dichromate solution, the quantity of iron present in a certain substance can be calculated to the greater accuracy as compared to the KMnO4. But mainly in this case, using dichromate solution, it has its own yellow or orange color. The change in color will create problem, and definitely the color change from yellow to green. So in this reaction we have to use an indicator. The color of indicator and color of chromium 3 ions might create a little bit trouble for the identification of the end point. That's why for the redox reaction normally we don't use potassium dichromate solution as an oxidizing agent. Rather we use KMnO4 solution, which is more visible, and there is no need to use indicator. That's why that titration of redox titration uses KMnO4 instead of potassium dichromate solution. These are the redox titration. Using redox titration, we can calculate the volume of reductant or oxidant used and can calculate all the subsequent questions regarding molar masses, percentage purity, or all other which are associated with them. And all these titrations involves redox reactions. Now, the next topic is ligands. Ligands and complex formation. For example, ligands. What are ligands? Ligands are atom or group of atom which contain pair of electrons that can be donated to the central metal atom forming a coordination complex. These ligands are the species which contain primarily lone pair of electron or negative charge. Now, the ligands are of so many types that might be neutral ligands. Neutral means just like H2O. H2O contains two lone pairs of oxygen atom but no charge. That's why this is neutral. Similarly, NH3. NH3, a lone pair, is also present on nitrogen and having no charge. That's why this is called as also a neutral ligand. But there are some ligand containing charges, for example, and those are chloride, for example, cyanide, for example, diaminoethane, NH2CH2CH2 and NH2. Similarly, there are so many other ligands present which contain lone pair of electron or the pair of electron with charge. Now, diaminoethane is also a neutral ligand having no charge but two nitrogen atoms containing two lone pair of electron. Depending upon the number of lone pair of electron, the ligands are of many types depending upon the number of electrons. These are called as, for example, if one lone pair is present, if one pair of electron is available is for donation, then this will be called as monodentate monodentate ligand. If a molecule contain two lone pair of electrons, just like diaminoethane, two lone pairs are present in one molecule, this is called as bidentate ligand. And if a molecule contains more than two lone pair for the coordinate covalent bond formation, those are called as polydentate ligands. That is, the common example is EDTA, ethylene diamine tetraacetic acid, EDTA. This is considered as a polydentate ligands. One molecule of EDTA can build up more than two coordinate covalent bond with the central metal ion of a transition metal. That's why these are called as ligands. Now, when ligands form coordinate covalent bond, then they form coordination complex, and those coordination complex are formed by the all ligands surrounding central metal ions. I think